the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 59, where today we have Dr. Miriam Diamdond here with us, a dark matter experimentalist. So, before we even start, Miriam, maybe you want to introduce yourself to our audience. What is it that you do? Also, a quick disclaimer, I shouldn't cut you off, but she is our professor in thermal physics. Parker and I both had that shared class, so that was a wonderful semester. Thank you for teaching us. And maybe you want to introduce yourself?
Sure. So I am an assistant professor at the University of Toronto Department of Physics, and my mission is to convince you all to join the dark side.
With dark matter, of course.
Yes, of course. And especially with Star Wars Day coming up soon.
True.
May the dark side of the Force be with you.
Oh, this will be... No, it's going to be up on Monday. Oh, if only. That would have been really cool. If it was up on Tuesday, May the 4th. So that would be pretty interesting. Yeah, Star Wars Day coming up soon. So to everyone celebrating, let's go. So,
Right,
Parker, let's get the news
before
going.
we actually get into the podcast, as always, we have a little bit of news. YouTube. No, we were already above 500 on YouTube. Yeah, that's true. Recently, we hit 7,700 followers on Spotify. So thank you so much, everybody that's been listening to the podcast and commenting on YouTube. We do have a comment of the week, as always.
Let's hear it.
So this comment actually comes from Kathan Shaw. They say, before starting out the series on relations, you guys should consider an episode on trigonometry because they deserve one. Now there are around 500 subs, so congratulations on 500 subscribers. Thank you so much. And the reason why this is the comment of the week is because we are actually picking suggestion for next week's topic for the podcast. So thank you.
Trigonometry. That's something we never thought about that. Like we actually discussed a lot of things in these 59 episodes. Never thought of trigonometry.
Well, actually, just before we came on air, you were saying to me it was okay if I went off on a tangent. And I said I might go off on a sine over cosine instead.
Tangents is something we love on this podcast, for sure. That's something we're almost known for on here. So, yeah. So, maybe we can kick off the podcast with the classic question, as always. So, Miriam, how did you get into the field of science? Like, what inspired you maybe as a kid? Was it an event, a series of events that led up to it? What was the whole deal?
Well, you see, when I was young, my ship got stranded on a deserted planet. And when I was struggling to survive, I learned that I had the power to tap into the dark side of the Force.
Very
and
rough.
No. Seriously though, I have been fascinated ever since I was a very young child with how the universe works. I was just always wondering, why do things work the way they do? What are things made of? If I keep taking things apart and I split things, into smaller and smaller pieces, what will be, the tiniest thing that I can imagine? What is, the most fundamental Lego building blocks of the universe? I was also fascinated with things like time travel. I always wanted to build a time machine. When people asked me what I wanted to do when I grew up, I used to say, I want to invent a time machine.
Wow.
But then I realized that if I do succeed in building this ultimate time machine, I would just go back and give it to myself, and therefore I would already have it. And since I don't already have it, maybe I'm doomed to failure. Anyway, so that's when I realized maybe time travel was more complicated than I thought. And then I heard about things like black holes from various series on television, and I got really fascinated with that for a while. And then I guess I was in about grade 7 or 8 when I got obsessed with particle physics.
Wow, that's pretty young
Yeah,
to test
so
an
I read some
article.
articles in Scientific American, and then I read a book called The Elegant Universe by Brian Greene.
Oh, of course.
And
Amazing book.
yeah. And so I was obsessed with particle physics ever since then. It was like love at first sight. It was, I just knew that this was the love of my life. In high school, I hosted physics tea parties at lunch, and it would be an Alice in Wonderland Mysteries of the Universe thing where we would watch something like those Nova documentaries, which at the time had just come out. um, and meanwhile, we would have iced tea and talk about how weird the universe was.
That sounds like a fun science group, like like a sciencey thing to do. Sit together, like watch Cosmos, for example. I remember, like I used to
Exactly.
do that with some friends. That's always a classic. So yeah.
Yeah, Cosmos didn't exist yet at that time. It was, I
Oh,
think,
I guess not.
yeah,
I guess not.
it was Brian Greene who was doing Nova specials on
That's cool. That's cool. So he was
Elegant
much
Universe
bigger
stuff.
at that time.
Yeah.
Mm-hmm. For
Yeah,
sure.
yeah. And then also at that time, the Large Hadron Collider was in the process of being built, and I would log on to the CERN website using my dial-up internet. um, and check out the latest on the plans for the super collider and so forth. And then I was very lucky that as an undergraduate student, I got the chance to do some summer internships with the original Sudbury Neutrino Observatory project. And then that ended up later winning the Nobel Prize. I was very fortunate to have had Art McDonald as my mentor, actually, a few years before he became famous as a Nobel Prize winner.
Mm-hmm.
And so I've been very lucky to have a lot of role models and mentors throughout my career.
Yeah, I was gonna mention the Art McDonald thing because that's huge. Because the Breakthrough Fundamental Prize and the Nobel Prize as well. And I saw the collaboration and then Miriam Diamond over there. I'm like, that's amazing. So you work directly with, okay, so by the way, for people that don't know this Nobel Prize, I believe, and I still remember, so Dr. Art McDonald is from Queen's University, and in 2016 he won the Nobel Prize for proving almost that neutrinos have finite mass. Like that was, if I'm not mistaken, the essence of the prize, correct?
Yeah, so technically it's that neutrinos come in 3 different flavors and that they oscillate between those flavors. And that flavor oscillation also implies that they have non-zero mass.
Because there was also a common confusion, I believe, of how neutrinos can keep switching from like electron to tau, and they can keep going
Yes,
back and forth.
exactly.
So that
Yes.
was also something proved. So that was an amazing, moment. And I still remember reading up on it into it, when this happened, and to find out that you were part of it, it's amazing.
Yeah.
It's amazing. So what was that experience like, though, working with, like, or did you work directly with Dr. McDonald?
Yes, yes, I did.
And so what was
Yeah,
that
so
like?
by
That
the
must have been amazing.
yeah, so by the time I came on board, though, the actual experiment was already finished, and it was just data analysis that we were doing. So I was not actually down there in their mine shaft while the data for the original snow project was being collected. That would
Mhm.
have been really awesome, but I would have needed a time machine to do that.
Yeah.
So what exactly is the experiment? Like, how do you even collect this data to then analyze and figure out that neutrinos are cycling between these flavors?
Okay. So essentially, the way that we have gone about detecting neutrinos over the years has been to have a really large tank of something. And even though neutrinos interact very, very rarely with the rest of matter, so a neutrino can go through an entire light year of pure lead and have only a 50% chance of interacting.
Oh wow.
Yeah, but just because there is such an unfathomably huge flux of neutrinos coming down from the sun constantly, um, that even if there's a very, very tiny chance for any individual neutrino to interact, there's just such a huge number of neutrinos that if you then build a large enough tank, and if you wait for a long enough period of time, you will get a significant number of neutrino interactions.
Sorry to cut you off, but maybe you want to explain what a neutrino really is.
Ah,
I don't
yes.
think we've ever actually been through this. So maybe
Oh,
that
you've
would be
never
like an
had a
interesting
neutrino?
explanation.
No.
Okay. So the standard model of particle physics is basically what tells us what all the different types of particles are and how they interact with each other at the most fundamental level. And so there are a few different types of fundamental particles. There's 6 flavors of quarks, where most of the ordinary matter that is around us is made up of just 2 of those. There's up quarks and down quarks.
A baryonic matter.
Yeah, yeah. And then we can produce the heavier quark flavors in, for example, supercolliders. And then there are leptons. And so the 3 electrically charged leptons are the electron, the muon, and the tauon. So the muon and the tau are basically heavier versions of the electron. And then each of those has a partner which has no electromagnetic charge, and that's a neutrino. So there's an electron neutrino, muon neutrino, and tau neutrino. And so the thing about these neutrinos is that they have tiny, tiny masses. We originally thought that they had 0 mass, and it was quite a surprise that they did actually have teeny masses. They, as I said, have no electromagnetic charge. They have no strong force charge, so they interact only through the weak force. And so that's why they can go straight through normal matter and usually not even leave a trace that they were there. And they are produced in nuclear reactions, for example, like what happens at the core of the sun, because it's the weak force that governs, for example, neutrons turning into protons and electrons, or protons and electrons combining to produce neutrons. And so basically, when we look at the sun and we think of it as this brilliant source of photons, actually you have to imagine that neutrinos are constantly streaming out of it too, because those same nuclear reactions that produce the light that we see produce huge fluxes of neutrinos. And so for quite a while, we had this thing called the solar neutrino problem, which was that we had some astrophysical models that predicted the number of neutrinos that should be produced in the nuclear processes in the sun. And we thought we had a basic understanding of how those nuclear processes worked. In other words, how the sun shines. And then we had some very primitive neutrino detectors here on Earth, and they were only predicting about a third. They were only detecting about a third the number of neutrinos that we thought they should be finding based on what was coming out of the sun. And it turned out this was because those detectors were only sensitive to the electron flavor of neutrinos. And neutrinos actually spontaneously oscillate between the 3 flavors as they travel. So even if they start out as electron neutrinos, because of basically the weirdness of quantum physics and uncertainty, it's a mismatch of eigenstates, technically, they have a certain probability of spontaneously turning into one of the other flavors. Even in vacuum, even while they're traveling through completely empty space.
And are they equally likely to be in each one of these 3 states?
So that's actually one of the things that we've been working very hard to study over the past couple decades, is the so-called neutrino oscillation parameters. And there is a matrix that describes essentially the probability of each flavor turning into each of the other flavors. And so the answer to your question is essentially no. It's not exactly equal probabilities, and you have to consider that the mass eigenstates and the flavor eigenstates are mismatched. So each mass eigenstate, because we now know that the masses are not zero, each mass eigenstate is a different mix of flavor eigenstates and vice versa.
Okay, so it doesn't like directly depend on each other. So like it could, so that's why it can be like disproportionately equal. That's why it doesn't have to be all equal probabilities, what you're saying.
What I'm saying is that the terms in the 3x3 matrix that describes the oscillation are different sizes.
Are different sizes. Okay. Okay. So okay. Okay. Yeah. So okay. Sorry. Continue.
Yeah. And so basically the Sudbury Neutrino Observatory was the first neutrino detector that had the technology to detect all three flavors. And so we solved the solar neutrino problem by seeing that a third of the neutrinos that we were catching were electron flavor, and approximately 2/3 were muon and tau flavored, and that if you combine all of those together, you get an observation that matches what had been predicted by the astrophysics models of what was coming out of the sun. So this was the solution to the solar neutrino problem.
And what is the fundamental difference? Like when you said it can only detect electron neutrinos, like what is the fundamental difference between like detecting an electron neutrino versus that of a tau or a muon?
Right. So basically it comes down to what is actually happening in the interactions in this giant tank. So first picture in your mind a giant sphere that contains literally a ton of heavy water. And then you put photomultiplier tubes, which detect very small flashes of light, all around the outside of this transparent sphere, so that anytime there's a tiny flash of light inside the sphere, one of these literally thousands of photomultiplier tubes on the outside will pick it up. And in fact, several of the photomultiplier tubes will probably pick it up at the same time. And then you put this whole thing on a support structure and you bury it 6,800 feet below the surface of the Earth. And the reason we have to bury it is that otherwise cosmic rays and all kinds of other stuff happening on the surface would, make things constantly flash inside this giant transparent ball. And so, yeah, we put it at the bottom of this deep, dark mine shaft where almost nothing else is happening in it. And we wait for every once in a while a neutrino to travel right through the rock and travel right through the acrylic that makes up the sphere and interact with something in the heavy water. So then the question is how exactly is that interaction working? And so it can interact with an electron in one of the hydrogen atoms, usually, or it can interact with the nucleus. And so this basically means that if it's an electron neutrino, it can go through what we call a charged current reaction, where it interacts with the electron, because each neutrino can basically have a special interaction with the charged lepton that it's paired with. So a muon neutrino or a tau neutrino will not interact with an electron through the charged current reaction that an electron neutrino interacted. Okay, but all three flavors can have what we call neutral current reactions, where it basically gives the whole thing a shove over, and so you get this tiny sort of recoil effect that you see from sort of the nucleus as a whole. And so essentially you can count the number of neutral current reactions, and you can compare to the number of charged current reactions. And then that gives you, what is the ratio of electron neutrinos to the ratio of all of the different flavors of neutrinos.
Oh, that's such a cool way to do it.
Yeah, right.
That's such a cool
Yeah,
idea.
and by the way, what do you mean by heavy water?
Oh, okay. So water is H2O. So the H, which is hydrogen, is usually just one proton and one electron. But if instead it is deuterium, then it has a neutron.
Mm-hmm. So
Okay.
that water is basically made with deuterium instead of
Yeah,
uranium. Oh,
yeah,
that's cool.
yeah. And actually, what you have to watch out for is that there is a third naturally occurring isotope, which is called tritium.
Mm-hmm.
That has yet another extra neutron in it. And that one's really bad for experiment because it's radioactive.
Mm-hmm.
And anything that's radioactive also sets off a signal in the detector. So we actually have to do a lot of effort to get rid of all the radioactive contamination. We even have to be careful about stuff like radon that is hanging around in the bottom of the mine shaft for the same reason that radon hangs around in your basement. It's just a naturally occurring isotope in the earth. But then we also have to worry about the tritium that is actually in the water. And so we had to develop a special, essentially, filtering system that gets rid of everything except maybe one atom of tritium in an entire ton of heavy water, which is really difficult. And the heavy water itself, we actually borrowed from decommissioned nuclear reactors because deuterium is also used as a moderator in, for example, the old style CANDU reactors. So Atomic Energy Canada was kind enough to loan us their unused heavy water, which otherwise would have cost us, I don't know, something like $1 million at the time.
Oh my.
Probably well more than that now, accounting for inflation. Yeah.
Because that was so the experiment. I believe the paper was started to be written in 1984, right? Or
Yeah. I mean, it kind of, it's hard to define an exact start date for it.
but around like
Because
maybe the 1980s.
But the 1980s was when they started planning
okay.
the experiment. Yeah.
Okay.
So, I mean, it took a long time to go all the way from planning to then actually, because when they first started planning it, all you had was this giant hole in the ground with this really deep mine shaft where they were like, it's still an active mine. They're pulling mostly nickel and some copper out of the bottom of the mine. So you have to plan for, okay, how are you going to dig a cavern and make it a clean room space? Like not just a place where you can do science, but a world-class clean room space at the bottom of the mine shaft. And then you have to think about, okay, the actual detector. So how are you going to construct this giant acrylic sphere? And then get all the photomultiplier tubes that you need on the support structure and assemble it all underground, right? And then just all of the technical difficulties of, the electronics readout for this kind of system. And then, as I said, getting rid of all the backgrounds like the radon, tritium, and so on. So there were several stages of planning this, and it took several years to plan. And then the actual data taking happened in 3 different phases, and each phase ran for a couple of years in total. So the first phase was just with the heavy water, and then the second phase, they actually added a certain type of salt into it. Like we literally sprinkled salt into the detector. Wow. And then for the third phase, we built these tiny little spherical detectors called NCDs, neutral current detectors. When I say tiny, I mean in comparison to the entire 1-ton tank. Compared to a person, an NCD is actually a significant size sphere. And we basically put them on strings and we lowered them into the sphere. And as their name implies, they basically allow us to detect neutral current reactions with higher efficiency.
Okay, so I think there was a small glitch there. I think everything should be up and running now. My audio was a little dodgy. So I was asking basically about how this experiment, everything that about this whole heavy water situation underneath the ground has basically almost proven that the neutrino now oscillates between these 3 states. So where was the proof? Yeah, so where was the proof of the fact that they have non-zero mass? Was that also in this same experiment?
So basically that came when you combine our results with those of a partner experiment called Cameo Candy, which is why Snow and Super K shared the Nobel Prize. And it essentially comes down to this whole idea of the mass eigenstates being mismatched with the flavor eigenstates and the neutrino oscillations happening because you have these different mass eigenstates. If they're all zero, then that whole mechanism doesn't work in the same way.
Oh, so it's simply by the laws of physics, it cannot be zero if they're all oscillating.
Essentially, yes.
Okay. That's a pretty nice deduction from that experiment.
Yeah, as I said, it's a little more complicated than that. You have to combine our results with some slightly different results that came out of the Super K partner experiment in Japan, but that's the essential idea behind it.
Fascinating. And so I think at this point in the podcast, I'd like to steer the discussion into the direction of dark matter.
Yes.
Because, of course, you are a dark matter experimentalist, so might as well ask our questions. So first of all, just for our audience here, maybe give a little rundown about dark matter and why it's so mysterious and maybe why it's important.
Okay, so I guess I'll start actually with why it's so important. Our current estimates indicate that about 70% of the universe is dark energy, and 25% is dark matter, and about 5% is standard model stuff. And so that means that there's about a quarter of the universe, or about 5 times more than ordinary matter, of this dark matter stuff. And essentially, we have various different lines of evidence that indicate that the dark matter does exist. It originally came from astrophysics observations of basically how large astronomical bodies were gravitationally interacting with each other. And you can make some fairly simple predictions based on even just the Newtonian relationship between mass and how things move under the influence of gravitational force, to figure out that in things like galaxies and in clusters of galaxies, there must be a lot more matter there than what we can see. In other words, much more than the luminous matter. Otherwise, things would not gravitationally clump together as much as we see them doing. And so clusters of galaxies would fly apart, and spiral galaxies would exhibit what we call different rotation curves. So in other words, if you look at the radial velocity of stars that are near the outer parts of those spiral galaxies, based on their speed of rotation, there must be more matter within the galaxy holding them there than what we can see. And then there's been also observations of cosmic microwave background radiation, and some simulations that we've done for cosmology for large-scale structure of the entire universe. So by this we mean on the largest scales we can imagine basically how even clusters of galaxies seem to arrange themselves in these huge filaments. And then from the particle physics point of view, we have been suspecting for quite a while now that our standard model, as successful as it has been in many ways, is incomplete. There's some basic issues with the mathematical foundations of it. For example, why does the Higgs boson have the mass that it does, and why is the Higgs boson stable? Why is this basically hierarchy of particle masses the way that it is? So we have some particles like the Higgs, which are quite heavy, and then we have the various flavors of quarks, where the top quark is much, much heavier than, for example, the up and the down quarks. And then we have the electron and the muon and the tau, which are quite a bit lighter than, for example, the proton. And then we have the neutrinos, which have these ridiculously tiny masses. So we've got these particle masses all over the place, and we have the Higgs that is giving all these things mass, but the Higgs itself has a mass that is about 125 times that of the proton, and it just seems very strange. It doesn't all really hang together in a way that should be stable. Basically, it looks to us like the Higgs mass should not be stable at the value that it is. And we have no idea why the rest of the particles have this weird spread of masses that they do. And similarly, we don't know why the gravitational force seems to be so much weaker than the electromagnetic force, for example. We think that we know how the electromagnetic and the weak force combine at very high energies. So they combine into the electroweak force, and we think maybe we can even combine that with the strong force and do some sort of a grand unified force, and then we have no idea what's going on with gravity. We don't really know what's going on with the fact that we have a matter-dominated universe, rather than having had all the matter and antimatter just annihilate into pure photons, basically. So we have some sort of a matter-antimatter asymmetry happening that we don't entirely understand. This is also known as charge parity violation. So there's all these mysteries behind the standard model. And so a few decades ago, it was realized that some of these standard model mysteries could be solved by adding extra particles, and that those particles could also be what makes up the dark matter, because they would have very feeble interactions with the existing standard model particles. And so this kind of gave birth to dark matter searches as a combination of astrophysics and cosmology motivation and constraints from what we actually see in terms of, how much dark matter there should be in order to make the universe hang together the way it does, but not make it collapse back in on itself. And then the particle physics side of what might we need in order to complete the standard model and have things make more sense. And actually, for a while, people thought that neutrinos might be dark matter. And neutrinos were, in a way, a form of dark matter in that they had quite feeble interactions with the other standard model particles. And they did have some non-zero mass, and they did make up some very, very tiny percentage of the mass energy budget of the universe that could not be accounted for by things that we could see, essentially. So you could think of them as sort of the first component of dark matter that we ever found. It just happens that they only make up something like 1% or less of the mass energy budget of the universe. So there's still all this other dark matter out there. But the same detection techniques that we used for neutrinos could be adapted and refined to look for dark matter particles that sort of behaved in a similar way, except that their interactions were even more feeble, for example, or they had higher mass, or they were even trickier to find for other reasons. So that's how I sort of started my career in neutrino physics and then ended up in dark matter physics. It was sort of my idea of leveling up. You take, one type of particle that was really hard to detect, and okay, now we found it, and now we can actually study in detail some of its properties. Okay, but now we got to get to the next level of sensitivity where we can find particles that are even.
So, yeah, sorry, continue. You're saying? Yeah, so I just want to say before we get into how dark matter is actually detected, because I believe like currently you're working on like super CDMS and like previously you've worked on like the Atlas projects and stuff like that. Before we get into that, because I do want to ask something that you were mentioning about the standard model like just now about how we try to we're still on on grips with the whole gravitational force. Now, my understanding with general relativity and the standard model is that the standard model is kind of going against the idea that gravity simply is a fundamental consequence of space-time curvature. And right, because the graviton, the hypothetical graviton, is kind of going against general relativity and saying that no, gravity is not a curvature of space, but it's actually a force that's carried by the graviton. So is the standard model basically refuting general relativity, and what is your opinion on it? Like, would you believe that the graviton exists, or are you more inclined to believe that, well, gravity is simply space?
Okay, so it's a little bit more complicated than that. In that, okay, I will say that quantum physics and general relativity do not play well with each other. And of course, the standard model is built in large part on quantum field theory, which is built on quantum physics. And so there are some clashes between quantum physics and general relativity that then show up, when you go all the way down the line, so to speak, to the foundations of the standard model. That being said, though, when you have, so basically when you study gauged quantum field theory, you end up getting a mass zero spin 2 particle, which is called the graviton in the standard model, that has properties that exactly match what you need from general relativity to basically form the mathematical structure of the gravitational field. So it's not exactly incompatible in the way that you were saying. The problem is that when we try and find a theory of what we call quantum gravity, we get ridiculous answers like 0 or infinity, because of essentially the I mean, it's a little bit hard to explain why general relativity and quantum physics don't get along, but basically quantum effects that happen at the smallest scales, so things like a quantum foam where, particles pop in and out of existence and you have this very violent frothing sea of stuff, is very different from the general relativity sort of smooth vacuum idea. So when you try to actually carry out calculations that have this frothy quantum foam, and you try to translate that into the kind of smooth space-time background that general relativity requires, that's when you run into trouble.
Mm-hmm. Yeah, because general relativity, like it's also describing like as the term suggests, a more general view of space. Like it's not looking at your individual probabilities and particles, but it's looking at in general how would you view a space. But I mean that's not real. I mean I guess that is a very valid like difference in quantum mechanics and quantum physics. I'm aware is quite different from general relativity right now. But it's simply the idea behind gravity, I believe, that is differentiated between particle physics and general relativity, right? Because in general relativity, he doesn't even believe, or Einstein doesn't even believe, that gravity is an actual force, right? It is regarded as simply an effect of space. So just the way you view gravity is different in general relativity than what you do in particle physics, right?
Yeah, so it is a little bit different in that if you treat gravity exactly the same way as the other forces, there's some sort of a special link between gravity and space-time that the standard model in its current form doesn't entirely take into account. But there are a lot of ways that you can potentially get around that and make gravity seem more similar to the other forces. For example, if you add extra dimensions, through which the gravitons can propagate, but the other carrier particles cannot. And then if you, for example, translate the curvature of the extra space-time dimensions into properties of the subatomic particles that show up in our 3+1 view of space-time, then you can actually make gravity seem to behave a little more like the other forces. But yeah, there are also theories, I guess I would call them alternative or modified gravity theories, which treat gravity in a very radically different way, where indeed gravity is not necessarily a fundamental force at all, but it is, for example, emergent out of quantum entanglement effects, is one theory that's been going around.
Oh, what? That's pretty crazy.
Yeah,
coming from there.
Yeah, I don't personally subscribe to that theory, but it's some very interesting research. So yes, there are some people who say that we've been entirely on the wrong track with gravity all this time, and that, yeah, for example, it's quantum entanglement between particles that's causing this effect that we call gravity. And then there are theories under which there's actually another force that behaves similar to gravity, but only on very, very large scales. And so the gravity that we see is actually the combination of, a more fundamental gravity and an extra force. And so then, when we treat gravity as just one force, we're actually completely off base. And then in those theories, you don't necessarily need dark matter, or you need a different amount of dark matter, because basically the astrophysical observations that tell us dark matter must exist, well, they could also be interpreted as saying we have the relation between mass and gravity wrong, possibly because there's this extra gravity-like force that only operates on cosmic scales, so we never see it like on Earth scales, and that's actually what's messing up all of our astrophysics predictions.
Yeah, that's fascinating. Before we actually move on here, Ray and I, we know that all of our listeners aren't, university students, or maybe they're just high school students that are interested in what we're learning right now and what we talk about here on the podcast. And, the best way to actually, act on those interests is to, self-study. And we actually recommend using brilliant.org. They actually have a course on astronomy, and I actually recommend their course on knowledge and uncertainty, which actually plays into the experimental side of physics, where you do actually have to deal with uncertainty literally every single time you do an experiment.
Mm-hmm. Uncertainty is a big part of physics, and obviously with all these courses, and I think we've all always mentioned this on every one of these messages, the one thing Brilliant does is practice. So when especially with uncertainty, that's something that a lot of people coming into first year of university don't know about, because in grade 12, you never really touch on any uncertainty experimentally speaking. So it's always like a nice thing to know. And especially, because we're talking about, experimentally finding dark matter, it's always a cool course to check out. So yeah, go check out the link in our description below, or you can just go to brilliant.org/MPP. And yeah, you can check us out. And the first 200 members get 20% off their premium subscription. Why wouldn't you want 20% off your premium subscription? So yeah, so go check us out. Link in the description below. And yeah, thank you, Brilliant. So continuing on your very interesting experimental career, maybe you want to take us through a little bit of your experience in the ATLAS experiment. So what was it, and what did you do in that experiment?
Okay, so ATLAS, for people who have not heard of it, is one of the 4 main experiments at the Large Hadron Collider. And so this is the most powerful super collider ever built. And So essentially, we take protons and we run them round and round and round in a ring, going faster and faster. And we have one beam going in one direction, one beam going in the other. And at 4 points along the ring, we bring those beams together such that the particles going in opposite directions smash into each other. And there is a large detector around each of those interaction points, which basically collects all of the subatomic debris that comes flying out of that collision. So it's like the most extreme game of bumper cars you can possibly imagine, where you then have to gather up all of the wreckage after the crash in order to figure out what each of the cars was made out of before they crashed into each other. And so one of the most popular theories of dark matter, especially at the time that I started working on it, but even still a popular theory now, is known as weakly interacting massive particles, or WIMPs for short. Yeah, physicists like to give things cute little names like that. Yeah. And so the idea here was that this was something kind of similar to a neutrino, in that, you know, it had very feeble interactions with the standard model, but much, much, much heavier. So by much heavier, we are thinking like at the tera electron volt scale, which is about 1,000 times heavier than a proton, just for reference. And so the idea was
compared to like a neutrino, for example, how much would it be?
So a neutrino,
because I guess if we're comparing it to neutrinos anyways, like, is there like a times like 10,000, 20,000 times more massive? Like, what is there a number?
Yeah. Okay. So first of all, I should probably explain why I'm giving masses in terms of electron volts.
Yeah, maybe. Most people might be used to the kilogram.
To the kilogram thing, yeah. So basically, the problem is that mass scales that we use in everyday life, such as a gram, are just absolutely enormously huge on the level of subatomic particles. And so we would keep having to put these like times 10 to the minus something really big exponents after our mass measurements of subatomic particles if we expressed it in grams. So instead, we have this unit called electron volt. It is actually a measure of energy, but mass and energy are interchangeable according to E equals mc squared. And it is the amount of energy that's gained by an electron when the electric potential is increased by 1 volt. And so this is something like 10 to the minus 19 joules. Okay, so it's a tiny, tiny amount on everyday scales, but it's very convenient for dealing with subatomic particles because, as the name suggests, you know, it's on the level of processes that the electron typically undergoes. And so then a neutrino is something like 500,000 times or maybe 1,000,000 times less massive than an electron.
Wow.
Yeah.
Very tiny.
Yeah.
Very tiny.
Yeah. Yeah.
And then as you just said, oh wait, you just said our WIMP is like thousands of times more massive than the proton, which is
right,
exactly.
like
20 times more massive than the electron. Oh,
right,
right,
right, exactly, because an electron is about half of a mega electron volts, and a proton is about 1 giga electron volts. So there's like a 500 times mass difference there, and then there's So okay, yeah. So that's one of the reasons I was saying earlier that, you know, the masses of the subatomic particles are really wonky.
For sure.
Really, really wonky.
Intuitively, I would think that the mass of a particle is, you know, proportional to its size and also its probability of interaction with other particles.
Right, but it's totally not. It's totally not, because we think that all particles are point-like. In other words, they have no actual spatial extent of their own. If you ask a string theorist, they will tell you that a particle is actually a tiny little loop of string that's vibrating, and so then it's actually not just a point. It has some spatial extent to it. But in any case, its mass actually has nothing to do with its spatial extent. It has something to do with what vibration mode the string is in, even in that case. And then if you treat it as a point-like particle, of course, there really is no concept of size that you can tie to mass that way. And then in terms of the interaction strength, well, there's different forces by which it can interact. So there's the strong force charge, the weak force charge, and the electromagnetic charge, and those are not related to the mass on any fundamental level. The only thing that's related to the mass is basically what gravitational force it exerts. Which, on the level of subatomic particles is essentially negligible. So anyway, so we were looking for these weakly interacting massive particles, so they're very, very, very heavy on the scale of subatomic particles, but they interact extremely feebly. So it's kind of a weird combination that way. And then the idea would be that we hadn't ever observed them directly before because we had not been smashing things together with enough energy to produce something that massive. And so the hope was that, at the Large Hadron Collider, the most powerful super collider ever built, we would succeed in making these WIMPs for the first time. So since, of course, when the WIMPs are produced, they generally pass right through the detector. We still wouldn't see the WIMPs directly. We would see some sort of a signature, some sort of a fingerprint that they were there. So something like missing transverse energy, like when we reconstruct all of the rest of the visible particles in the event, we see that a bunch of energy has just gone missing. And by conservation of energy, it can't just vanish. So, some particle must have walked away with it. Or something like a displaced vertex, where if the WIMP, for example, then decays into other particles which are in the standard model, you would see standard model particles seeming to pop out of nowhere partway through the detector. Or the other way around, if a standard model thing suddenly seemed to vanish for no reason, well, it can't just vanish. It must have turned into something invisible. And so I worked on basically one category of these searches, which were called lepton jet searches, to look for one category of these heavy dark matter particles. And in run 2 of the Large Hadron Collider, we did not find them. The way that we like to say it is that we set world-leading limits or constraints on what dark matter particles could be, because of course every time that we do not find dark matter, we still learn something, because then we learn what dark matter is not, and by process of elimination, that is still helpful knowledge to have. So I always resent it when people say, "Well, you failed." I'm like, "No, we didn't fail. We just found out what dark matter isn't."
But I thought that WIMPs is still like a valid theory almost for
Yes.
dark matter, or is it just not? Okay,
Yes.
so it's still
Yes. So WIMPs are still valid, but not in the part of the WIMP parameter space. So basically, parameter space is the term that we have for if you make a plot with the mass of the particle along one axis and the interaction strength along the other axis. So we basically ruled out a large part of WIMP parameter space. And the part that we ruled out was the part that a lot of people considered to be most likely or most favored. People's favorite part of parameter space. But there is still a fair bit of WIMP parameter space that is unexplored. Basically, I during the course of my research became increasingly convinced that we were sort of looking at the wrong end of the mass spectrum, and that actually, instead of looking for something that was really, really heavy, I should be looking for something that was not nearly as massive, probably not quite as light as the neutrino, but something probably lighter than a proton, but that just had even more feeble interactions than the neutrino has.
And it's funny because when Rayhan and I were learning about WIMPs this past semester, I had this realization where it was kind of like, oh, we don't call it dark matter because it's not bright. We call it dark matter because it literally just like goes through our eyes and we just can't see it whatsoever.
It goes through pretty much everything.
Yeah,
Yeah.
everything, not just
Mm-hmm.
our eyes.
Yeah. And
Yeah.
I mean, actually, if you think about it, there are trillions of neutrinos going through every little patch of your skin every second from the
Mm-hmm.
Mm-hmm.
sun. They're just constantly going
Mm-hmm.
right through you, and you don't even notice. So, yeah. So, yeah. Similarly, there would be dark matter all around us. There'd be this dark matter halo um, that Earth is constantly traveling through, if you want to think of it that way. Sort of this dark matter wind.
Mm-hmm.
It's equally
Mm-hmm.
valid to say that we're moving relative to it, as it is moving relative to us.
Mm-hmm.
So, yeah. So,
Because technically dark matter would be, well, almost everywhere in the galaxy, and I believe also a big part of like your CDMS research and the like super CDMS research, which is basically like the neutrino experiment. It's an underground, it's a glorified underground water tank, basically.
so actually, Super CDMS is not a water tank. There are a
Oh, it's not
few.
the water tank. Okay.
No, so there are some other experiments underground right now that use giant tanks.
Yeah.
It's not water that they use anymore.
Oh, I thought they did use water for dark matter,
Um,
because there was one that I remember
so they
seeing where this
use
one on this TV show where this
um,
one
uh,
guy.
so
Yeah.
so the actual detection medium is either argon or xenon. But then they take that tank and they surround it often with water, and the water is essentially to act as more shielding. Yeah,
For sure, because I
yeah.
remember seeing like this one I don't know if it was like a TV show or like it was like an episode where this one person was talking about his dark matter research, and he was like taking the cameras like into all of these tanks and stuff, and they
Yeah,
were showing. I'm assuming, yeah, I think now you're right. I mean, you're obviously like it's surrounded by water, and
yeah.
the actual element itself that it's interacting with is something like a radioactive gas. So I
No, it's
believe
actually the opposite of a radioactive gas. It's a noble element. So the thing
noble, sorry,
about
noble, not
radon,
radioactive. Noble,
yeah,
yeah, yeah, sorry, I mixed them up. I mixed them up.
yeah. So something
Krypton,
like,
argon,
yeah, so
noble, yeah, not radioactive. Sorry, noble
exactly,
gas. And
exactly.
what was really sad was that this guy was talking about his experiment and how he had been working on it for the last 40 years and not found any detection of dark matter. So, like, I guess my question that I can form out of this sad story is, well, what do you think? Like, do you think this is the right way to find dark matter? Like, just waiting for something to interact? Or do you think there's a more, out there approach that we can do to find it?
Right, okay, right. So the first thing I'm going to say to that is that, okay, Super CDMS is not a giant tank of something.
Okay, sorry.
And
Yeah, maybe you want
part
to
of the
explain what
reason
that
for
is first.
that is that in order to build more and more sensitive things in the style of these noble element searches, it involves making bigger and bigger tanks of stuff, which means you then got to, purify all the extra stuff that you're putting in, and you've got to, build more and more support structures out of more and more materials, which have to be extra purified, and then you need more and more of whatever detection apparatus you're using, and more electronics readout, and so on. So basically what I'm saying is that I don't think giant tank of whatever projects are particularly scalable in terms of making them more and more sensitive. So that's why the kind of experiment that I work on actually tries to take advantage of quantum sensors. And so Super CDMS, which is short for cryogenic dark matter search, uses semiconductor crystals, which are only like this big each, and you can stack several of them in a tower that a person can stand next to and reach around. And they basically, instead of waiting for a dark matter particle to come into the giant tank, they wait for a dark matter particle to interact with the crystal lattice and set it vibrating. And there, we now have the capability to detect single electron hole pairs that are produced. And we can translate just a very small number of phonons, where phonons are quanta of vibrations in a crystal lattice, into a signal that we read out using these things called transition edge sensors and superconducting quantum interference devices. And these squids, as we call them, superconducting quantum interference devices, are actually
acronyms for sure.
Are actually the same things that some people are trying to use to build quantum computers. And the idea is that these quantum sensors are basically far more sensitive than any other such device we've ever constructed. And so my idea is to look to the very small scale and look to these quantum devices to get us better and better sensitivity to more and more feeble interactions. And then I've also sort of come to the conclusion that looking for things in a very, very quiet, low background environment, deep underground, is better than trying to pick out a dark matter signature or a dark matter signal from this very noisy zoo environment of high energy particle collisions that happen like in Large Hadron Collider. Because even if you do produce the dark matter particles, you have to pick out their signature from amongst, all of the other debris that went off in that extremely energetic collision. And when you've got just all this other stuff going on with, Higgs bosons decaying and radioactive stuff and, extremely high energy muons and gammas and all sorts of other things. And you have top quarks and bottom quarks, which are decaying into other quarks, which then decay into other quarks. And then you have neutrinos running all over the place, which also go straight through the detectors. And so even if you have, a missing energy signature, you then have to figure out, okay, well, was that just from the neutrinos? Because you've got neutrinos running around all over. And you have these events that are happening like every few tens of nanoseconds. And then in each of these events, you have actually bunches of protons which are colliding with each other, not individual ones. So you have what's called pileup of like potentially dozens of collisions happening at exactly the same time, pretty much. And then you've got to reconstruct the debris from all of those collisions and try to pick out, the very, very, very rare dark matter signatures. I'm not going to say that it's hopeless, but I think that it's extremely challenging.
Sounds very hard. Sounds like a lot of work.
That's basically my pitch for why I do the type of experiment that I do. So I think that basically quantum sensors in a very quiet, very low background environment underground is the most scalable way to go, and it gives us the best chance of actually picking out the dark matter interactions.
So you do believe this underground sensor is the way to continue to search for dark matter?
I do. Of course, I may be proven completely wrong when some other completely different type of dark matter search finds it. And so, I mean, I am always, how can I put it? I try to have a lot of humility when I say that, because nature tends to surprise us, and nature doesn't care what I think.
Very true.
Mm-hmm.
Very true.
That's right. Before this podcast, we were doing a little bit of research, and we came across your thesis. and in the title, we saw the word dark photons. Mm-hmm. And we just wanted to know, like, what is a dark photon?
So it is literally the dark side of the force. So
literally. That's nice. That's fun.
So the photon is, of course, the carrier particle of the electromagnetic force, right? And so the theory is that there might actually be multiple types of dark matter particles, sort of like there are multiple flavors of quarks or multiple types of leptons. So that instead of just one extra subatomic particle, maybe there's several extra related subatomic particles that are in this sort of dark sector. And maybe there is, as part of this dark sector, a force similar to electromagnetism, so I guess you could call it dark electromagnetism, that operates between those particles. So the dark sector particles don't feel standard model electromagnetism, and standard model particles don't really feel dark electromagnetism. And just like electromagnetism has the photon as its carrier, dark electromagnetism has a dark photon as its carrier.
Wait, sorry, this is a theory though, right?
This is a theory.
This is a theory. Okay.
This is a theory.
Yeah.
But according to this theory, then there would also be a tiny mixing between the standard model photon and the dark photon. And so then basically every once in a while you could turn a standard model photon into a dark photon, for example.
But where does that idea come from? Like the fact that they can just kind of turn into each other?
Oh, so the fact that they turn into each other, so it's basically if you work through the quantum field theory of this hypothetical
Okay.
dark photon, there's basically it's very difficult to avoid having it turn into a regular photon
Wait, so what
if
exactly
it's
is
a
this dark electromagnetic force then? Like, because electromagnetic force, like, I think about it as either visible or some kind of spectrum. So is there like a dark electromagnetic spectrum, and is there any visible? Like, I'm just trying to ask questions because I don't even understand what this dark force really means. Like, what does that
so when I say that the photon is the carrier of the electromagnetic force, okay, so you know that everything is both a particle and a wave, right? So the photon itself has particle-like properties and wave-like properties. Electromagnetism, classical electromagnetism treats it as just waves, right? But everything is both a particle and a wave. And so when you talk about the electromagnetic spectrum, usually that's shown to you as different wavelengths forming different parts of the spectrum, right? But by the de Broglie relation, right, every particle has a wavelength associated with it. For a massless particle, there is a relationship between the energy of the particle and the frequency, which is the inverse of the wavelength.
Mm-hmm.
And so the different wavelengths of the electromagnetic spectrum actually correspond to different frequencies and therefore different energies of photons. And so, yeah, similarly, dark photons can have different energies. And so then, yes, they would have a spectrum associated with them. What we call the visible spectrum is simply the range of photon energies for which our eyes operate as detectors. So our eyes are, actually, we've recently found that they can detect even down to single photons. So our eyes are some of the most sensitive photon detectors ever developed, actually, but only for a certain range of photon energies. In other words, for a certain range of wavelengths, and that's what we call the visible spectrum. And then there's, other parts of the spectrum that we use for radio transmissions. We call those radio waves. There's others that we use in microwave ovens, right? We call those microwaves. The really high energy ones we've labeled gamma rays, right? And then because red is the lowest energy on the visible spectrum, then just slightly less energy than that is infrared, and then violet is the most energetic, so just more energetic than that is ultraviolet, right? So that's how we've sort of labeled our visible spectrum. But of course, aliens would have labeled it completely differently, right? If they've got sensory organs, right? So that's kind of arbitrary. It's not based on laws of nature, right? How we split up the electromagnetic spectrum is just,
It's also dependent on our eyes and like
right, totally arbitrary,
I'm
right?
assuming like there's some insects and some animals on the earth that can view a lot more
Right.
colors. I believe some people can view like 100 million more colors than some people because they're born with like a different gene in their brain. So that's also like there are some people like that. That's pretty cool.
Yeah, it's not a
But I guess
different.
that's more color. That's not energy. I guess
Yeah.
that's a little different. But like, I
Well,
was just,
no, well, it is because color is just our interpretation of wavelength. Yeah.
but
So,
isn't like
well,
no, because what they are able to do is distinguish between more colors.
yeah.
Not like they can actually see more colors. They can distinguish between like millions of more colors than our eyes can.
Yeah,
So
so
like,
that
oh, that's
basically
a pretty
comes
cool.
down to like so what is the energy
Yeah.
resolution of the detector is basically what it comes down to. And
Mhm.
we kind of battle the same thing experimentally. How closely can you, or how precisely can you determine the amount of energy that, say, a single photon carries in the detector? So if you can distinguish colors more accurately, you're basically saying that you have better energy resolution in the single photon detector that is your eye.
So
Yeah,
moving back very temporarily to the dark photon, because
right.
I'm very intrigued by that. Why dark? Because in my understanding, the entire point of photon and light is, well, it provides light, no matter what, it's providing radiation. So to say dark photon, You know what I mean? It's almost like they're two
Yeah.
opposites being put together.
Yeah,
So
so
I don't
the
understand.
dark photon provides dark radiation.
Like, what
It
does that
is
even mean? Dark radiation? What is
right.
that?
So, okay, so as I said, it's a force that is similar to electromagnetism. And when you say that it's similar to electromagnetism, I mean that the carrier particle is a vector boson that is an SU1 group.
Yeah, so
Probably doesn't mean anything,
complicated stuff there.
but so
I just know the Higgs boson is scalar. That's what I
right,
know.
right, right, right. Um, so yeah, so it is basically another long range force. Okay, and so just like things have electromagnetic charge and some things interact with the electromagnetic field and some things don't, okay, then there's this other sort of dark electromagnetism charge where some things interact with it and some things don't. Um, and so it's so basically to us it's dark. We can't see it because the matter that our eyes and that our detectors basically are made out of only interact with the electromagnetic force, with things that are electromagnetically charged, not with things that are dark electromagnetically charged.
Then why do we even need it though? Like,
So
what
the
does
reason
it
that
play? Like, what does it help us with?
right, so
Just
it
to start
so
off with.
so it doesn't really help us. It helps the dark matter particles.
Oh, okay,
It's
okay. And
this,
where?
it's
Okay,
the
because
right.
it provides like a
So
spectrum for dark matter.
yeah, so basically because
Okay.
the dark matter particles are charged under this force, they can clump together differently.
Mm-hmm.
So it
Okay.
provides them a means besides just gravitational attraction to hold on to each other more tightly, which by certain astrophysics and cosmology models is advantageous. And then the other reason that it helps us though is that, as I said, there's this tiny mixing between the dark photon and the regular photon. So it
Mm-hmm.
means that if you produce a lot of photons, every once in a while one of them will go poof and turn into a dark photon. Um, and the other way around, every once in a while a dark photon will go poof into a regular photon. And so then the idea is that by examining the debris of these collisions in Atlas very, very carefully, we might be able to pick up evidence of the existence of the dark photon by essentially looking for what we call a displaced vertex. So it looks like something appeared out of nowhere, where actually what happened was a dark photon was produced in the collision, it went partway through the detector, then it just turned into a photon, which turned into some other stuff, and we detected that other stuff.
I'm excited for future experiments where we get like dark spectral lines.
That would be so cool. I'm imagining such an observation has not been made yet, right? Because that would obviously like change physics.
Nobody has ever observed a dark photon, no. There have been a couple observations that have been interpreted as possible evidence for the existence of, or at least consistent with the existence of dark photons. So there was one experiment that, for example, looked for transitions of a certain atom. So basically, if you have an atom trap and you watch very carefully what is going on with the transitions between energy levels and the emissions of photons from those transitions. If it's usually photons that are being emitted in the transitions, but every once in a while you can get a dark photon that's being emitted, right? Or if the presence of the dark photon changes slightly the exact energy levels of the transitions, you can try to pin that down with these really precise, basically atomic and molecular spectroscopy and optics experiments. So there was one, I guess you could call it anomalous result that came out of that a little while ago, but that's still, it's still being discussed whether or not this is, due to some other experimental effect that wasn't taken into account, or there's lots of other possibilities. But this was basically, if you want to look it up, it's the nuclear transition of beryllium-8 isotopes. And the idea was that this could be consistent with a it was something similar to a dark photon with a mass of about 17 mega electron volts. So it's been, but again, there's still a lot of other possible explanations going around for this. And then there's also some results that recently came out on what's called the anomalous magnetic moment of the muon.
G2, the G-2 experiment.
The G-2. So a dark photon was proposed, I think over a decade ago now, as a possible explanation for the muon G-2 anomaly.
That would be interesting. A
Yeah.
dark photon. Because they were proposing a redefinition of the standard model and adding or subtract. I believe it was adding a particle because there was an extra moment of spin, right? Like there was some extra spin that hadn't been accounted for.
Yeah, I mean, there's a lot of
0.00001 or something off, right?
Yeah, so there's a lot of different ways that you can theoretically account for this G-2 discrepancy. One of the ways that you can do it is by adding a dark photon to the standard model, essentially.
So
But
that solves this problem. That's interesting.
it could solve the problem potentially. The problem is that the part of dark photon parameter space that would solve this anomaly has already been pretty much ruled out by some other experiments that actually one of which I worked on myself. So it's not exactly the kind of dark photon that I looked for because I already ruled that out, but it might be something similar.
Might be something. Let's see. I think the future of dark matter is so bright. Like that's so funny. That's so funny.
Yeah.
I didn't even realize I did it till I did it. But anyway, I'm just so excited for the future of dark matter because I think it is not dumb, but it is still a lot more than matter in the universe. For those that might be wondering, matter is proposed to be around 3 to 5%, while dark matter is proposed to be around 25 to 28% of the universe. Right. So it's significantly more than what we see, than the baryonic matter that we can see. So if we have or are able to get any insight into what this thing is, I think it would truly, truly revolutionize the future of physics. So let's see, let's hope that, people like you, experimentalists in dark matter, can continue to keep working and, hopefully find that particle one day. Very exciting stuff.
Or group of particles.
It's
probably not a single particle.
Yeah. I mean, personally, I think it's multiple particles, just because if you think about the 5% or less of the universe that is the standard model, there's all these different types of particles that makes up the standard model. So then there's other stuff that's 5 times that much. So to think that that is all just one type of particle is kind of, I don't know.
There's a whole dark. Oh my, that would be so.
There's a whole dark universe happening.
Yeah.
At the same time, sorry. What did you say, Parker?
Oh, I said there's a whole dark universe with dark biology happening.
Yeah, that would be crazy. Like a dark standard model of particle physics, right?
Yep.
Like, that would be pretty interesting.
Yep.
That would be very interesting.
Yep. So actually, one of the other University of Toronto professors, David Curtin, works on what he calls these mirror models, where there's essentially this mirror version of the entire standard model that is dark. And there are these things, for example, called dark or mirror stars, which are stars made up entirely of this dark stuff. Yeah. And I mean, the sort of most promising original form of the WIMP model was supersymmetry, where every single standard model particle has a superpartner. Mm-hmm. And it is the lightest stable superpartner that makes up all or almost all of the dark matter. But then there are also all these other superpartners floating around. So, under that scenario, we've only found half of the fundamental particles.
I believe the supersymmetric relatives were also proposed to be the dark matter candidates at one point in time. Yeah, I do remember that. Yeah. So that was also a potential. Well, who knows, Well, supersymmetry is still far from off. So, that's going to be some interesting, very interesting years of science ahead of us. I think that'll always be true, though. Yeah. Right? Like science will always have some interesting years ahead.
Yeah.
That's just always how people advance.
Yeah.
And before we end the podcast, I believe you wanted to address something that is, predominant in the scientific community, something that we were talking about before we started this conversation, and something that I didn't really know existed in the science community. So maybe you want to touch on it.
Yeah. So as I'm sure everyone is aware of from the news media and from social media and just being aware of what's going on around us, really there are a lot of societal issues and turmoil to do with racism and discrimination of various different flavors. And when we think about what we can do in terms of anti-racism and in terms of equity and diversity and inclusion, that is important in the scientific community as well as in all other aspects of our society. And a lot of people, I believe, are under the impression that science in the 21st century has moved past having to worry about all that, and that, you know, all of our academic institutions and all of our research institutions give equal chances to everyone from equal backgrounds to be a part of the scientific endeavor. I wish that were true. Unfortunately, it's not. There is still a lot of discrimination of various flavors entrenched in our scientific institutions. One of the most obvious examples is gender bias. In my field, which is experimental astroparticle physics, it's about 90% male. So just, that is obviously not a statistical fluctuation. That is something that has been the case, or even worse, for many decades and is very entrenched in the system. Also, there is a systematic underrepresentation of visible minorities. And there's also a very serious socioeconomic factor that's involved, where people from lower income neighborhoods are less likely to go into scientific research professions. And a lot of that has to do with what educational opportunities are open to people, what barriers we are putting up, sometimes without even realizing it, all the way from the elementary school system through the high school system into the university system. That bias shows up, not just in terms of, for example, hiring of faculty members, but, in terms of, what science courses are offered at what schools, or what role models do you have? So were all your science teachers white males? If you kind of think about that for a minute, right? What about your professors? What about your TAs? And then even this idea of, if you're an experimentalist, you are still expected to do, even in the modern era where there's a lot more remote work possible, you're still expected to do an awful lot of travel, to do an awful lot of, really long shifts at, the bottom of the mine shaft or in the control room of a particle accelerator or whatever, that, maybe if you've got a family to take care of, right, maybe that's just not going to be possible for you. People in research are, shall I say, systematically underpaid at various points during their career. So people from certain backgrounds can't afford or are not given the opportunity to, get through the educational process of, being an undergrad and then a grad student and then a postdoc, and, you have to still have some way to eat and keep a roof over your head through all that. So there's this whole variety of entrenched factors that are keeping people from various backgrounds and of various genders and various races and even certain countries of origin out of our research community. And that really, really bothers me, because we spend a lot of time and effort, upgrading our detectors and our computers and our analysis technology and, our theory framework. And of course, all of that is going to help us make progress. But really, we still have these huge barriers to progress that we are allowing to just stand there and continue getting in our way by excluding such wide swaths of people from our research endeavors. And it's only when we get people from diverse points of view who bring in new ideas and new ways of looking at things that we are really going to maximize our potential as the human species overall in terms of understanding the world around us. And we have to understand that the scientific endeavor is a very human endeavor at the core of it all. And if we don't address these very human issues, we are basically going to keep hampering our own progress as a scientific community. So this is why, I put equity, diversity, and inclusion and anti-racism at really the top of my priority list in terms of things that I try to convey to the public as being really vital in advancing our research.
Mm-hmm. Yeah, thank you so much for that message, because, awareness is the most important thing when it comes to these types of barriers, especially in the science community, and we hope to use our, for what it's worth, our platform to spread this message, right?
Mm-hmm. Mm-hmm. I will tell you some interesting news, maybe for you and I still remember, and the audience. Originally, when we started, we had around 80 to 90% male viewers on our Spotify, because Spotify is the only one that lets you check like the metrics for some reason. And now we have almost 30% of our viewers female, because it was 85 to 90% male, and it was like 5 to 10% female. Now we have about 29 to 30% female. We have a percentage also in a non-binary and binary, or like the other genders as well, who are listening to our podcast. Anyways, the point being that we are in fact seeing that more people from more races, from more, or at least genders in this case, because I guess there's no race thing on Spotify, and it's good that that's not there. But I guess at least for the genders, like we already see that we are at least for us, it's improving. It's already been improving. Like we already getting like more girls, like more women that are responding, that are actively engaging in our podcast, like like emails, replying on comments and stuff like that. So it's really nice to see that. So it's hopefully. And I think we are going in the right direction. And I think we should just, continue, but maybe speed up a little bit. Let's see.
Right.
So thank you. Thank you so much for coming on this podcast today. Thank you for your time. It's been quite a long one. We've gone through some pretty interesting conversations in dark matter research and neutrinos and Art McDonald, which was a really cool guy. So thank you so much for coming on. And thank you. Awesome.
Yeah, we'd love to have you on another time to talk about dark energy, because I know we didn't really talk about that too much this episode. And also other questions that may have come up during this episode that we haven't had the chance to ask. So thank you so much for coming on today. For all of our listeners, make sure to follow us on Spotify or Apple or anywhere you're listening. Also subscribe to us on YouTube and leave a comment. You might be picked as the comment of the week on the next episode. Other than that, anything you wanted to say, Miriam?
No, just, of course, please stay safe and healthy, everyone. I know we're still in this pandemic, and people are getting very tired of staying home and not being able to see their friends, but please, everyone, hang in there, and please do continue to follow public health guidelines, and always put your health and those around you as first priority.
For sure.
And also to those listeners out there might have been wondering, where is the 100K Q&A? So don't worry about it. We will be mentioning it. We thought about mentioning it in this one, but we didn't, as you've already noticed. So it will be mentioned in the next podcast. Again, the point of the 100K Q&A is so that hopefully now, like, we're thinking about doing it live, so some of you guys can join us as we're answering the questions. So we're just trying to set up like a date where like people would be relatively available. So obviously not this episode, but by next episode, like, we should have a date and everything ready. So like, if you guys follow our Instagram, definitely just keep just keep looking at it, because we're definitely going to update it there. And also just stay tuned, because I will also be mentioning it on the podcast before it actually happens. So
All right. So yeah, this has been episode number 59 of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray, and we will see you soon.
Bye, guys.